So the topic that we are going to learn today is going to be called Equilibria, or equilibrium. Now, equilibrium, okay, when we look at equilibrium, basically, we are looking at reversible reactions. Now, how do we differentiate reversible reactions compared to normal reaction? You just need to look at this arrow. Okay, this arrow, okay, indicates that, okay, it can go forward and it can go backward. It means that, okay, this reaction CuSO4, okay, dot 5H2O, this is we call as water of crystallization. They can actually change into CuSO4 plus 5H2O. This one, you heat it up, the water of crystallization will go off. This is called hydrated copper sulfate. This is called anhydrous copper sulfate without the presence of water. And if you look at it detail, this is blue in color, the powder, it's blue in color. When the water of crystallization goes off, this is going to be white powder. And this anhydrous copper sulfate is actually one of the tests that we can actually use to find out the presence of water. Okay, the presence of water, you just put in water droplets into anhydrous copper sulfate, which is the white powder. The moment there is water, they are going to change into this hydrated copper sulfate. It means they can go backwards, which is going to be CuSO4. When they add with 5H2O, they are going to give you CuSO4.5H2O. It means that the color change is going to be from white powder to become blue powder. So this is a test, and it can go forward and it can go backward. So that's why this is called as reversible reaction. Now, not all the reactions are reversible, only certain reactions are reversible. Okay, another type of reversible reaction is going to be when you have two HI, okay, they can actually change into H2 plus I2. And the H2 hydrogen gas and I2 gas, they can combine to give you HI. Okay, so they can go forward, they can go backward. Okay, that is very important. Now, if you look at this, okay, do remember any kind of reversible reaction in a system of equilibrium, it means that they are going to continuously react. Okay, they will not stop. So we call it as, okay, a dynamic reaction. Yeah, it's a dynamic equilibrium. What is the meaning of dynamic equilibrium? It means the reaction will never stop. They will continue to react. Okay, it means forward reaction is there, reverse reaction is there. Although you don't see any changes in appearance, the reaction is still happening. Why? Because, okay, the rate of forward is the same as the rate of backward reaction. It means that once they have reached equilibrium, the state where they are stable, they are going to have the rate of forward, okay, this is the forward reaction, is the same as the rate of backward reaction. It means that the conversion to change into this and this product to change into this, the rate is the same. When this is the same, what you will see nothing. It means there will be something like there is no visible change. And because of that, okay, the concentration of the reactant, okay, the concentration of the reactant and the concentration of the product is going to be constant. Now, constant doesn't mean that they are the same. Constant means they are going to be not changing. Yeah, they are not changing. It will be the same value, but not same with each other. Yeah, please take note. And number 4, okay, in order to reach something in a dynamic equilibrium, you must make sure that all this is happening in a closed system. So we have two types of system, closed system and also open system. What is the difference between closed system and open system? Closed system, it means that nothing goes out nothing comes in. That is closed system. It means that if you have this, for example, you put the HI, let it react, give you H2 and I2, H2 and I2 go and change into HI, they reach equilibrium. You do not go and remove the H2, you do not go and remove this I2, or you do not even add anything over there. So it means nothing goes out, nothing goes in. Then they will be in a dynamic equilibrium. Now, what happens if you do some changes? I give you one example. If you have calcium carbonate, okay, supposed to change into calcium oxide plus carbon dioxide. This is solid, this is solid, this is gas. And let's say this one, okay, you put it in a closed system. Nothing goes out, nothing goes in. They will reach a dynamic equilibrium. Okay? But when you put it in an open system means solid cannot go out. But you put it in an open system means this carbon dioxide, as they are produced, they can go out as a gas. So when they keep on going out as a gas, what happens? Forward reaction, calcium carbonate, give you calcium oxide, give you carbon dioxide. The moment carbon dioxide is produced, they are going out. You remove it. Okay? Now, can the backward reaction happen as you are removing carbon dioxide? The backward reaction is supposed to be calcium oxide plus carbon dioxide to give you this. But carbon dioxide is actually going out. There is no carbon dioxide. So, the backward reaction, which is supposed to be carbon dioxide plus calcium oxide to give you this, is not happening. Okay, therefore, what happens? Only this reaction happens. Calcium oxide to give you carbon dioxide. This is going to be just a normal reaction. And this reaction will continue until it goes to completion. Okay, because why we are not going to have a reversible reaction? Why we do not have the backward reaction? Because you are keep on removing the carbon dioxide. Even though physically you are not removing it, but because it's an open system, they can actually move out. Okay, therefore, okay, you do not achieve this dynamic equilibrium. So in order to achieve a dynamic equilibrium, a reversible reaction must follow these 4 criteria. One is, okay, it must be dynamic. It will continue to react. Second, the rate of forward reaction must be the same as the rate of backward reaction. It means once they have reached equilibrium. And the concentration of reactant and the concentration of the product will remain constant, and it must be in a closed system. Let's look at it in detail. Let's look at it in this form here. This is going to be one example, okay, of reversible reaction. Now, let's look at it from the beginning itself. Now, from the beginning, you are just going to start from HI. You are not going to just go and put HI, I2 and hydrogen inside. No. You are going to start from HI. There is a particular concentration, okay, at the beginning itself. Now, at the beginning, let's say I give you a value, yeah? Let's say I use 1 mole. Okay, 1 mole. At the beginning is 0 and 0. Nothing was produced. It means you don't have any product at the beginning itself. Okay, let's say I'm going to actually draw a graph over here. And let's say this is going to be 1. And I am going to say this is going to be at time 0, yeah? At time 0, I have HI. And since this one is almost the same, I'm just going to show for H2 only. I'm not going to bother about I2. Okay, I2 is also the same graph. Let's say this is going to be H2. 0, starts from 0. Now, I let it react for some time. It's a closed system. They are going to react so that they are going to reach equilibrium. It takes time. You cannot just put them and suddenly they reach equilibrium. It takes time. Now, during that time, what happens? This is reactant. This is a product. Generally, reactant will give you product. It means that reactant, the concentration of the reactant will decrease to give you product because they are reacting. Okay. Now, when they are reacting, then only there will be some amount of H2 and I2 starts to form. When that is being formed, then only they are going to actually react to give you HI. Do you agree? Once you have H2 and I2, then only they can give you HI. So now what happens? Here, the HI, they will react. Okay, they will decrease. And let's say up to a certain time, yeah? So I just put at this particular time. This is the time where they are going to reach equilibrium. You see what happens at the time when they reach equilibrium. They will decrease, and then the concentration will become constant. Now, what will happen to the concentration of H2? Please remember, according to the ratio, this is 2 moles will react to give you 1 mole and 1 mole. If you react this much, you just follow my finger over here, yeah? If they react this much, it means that the amount that is going to be produced will be half of this value. Do you agree? Because 2 to 1, yeah? 2 to 1. So let's say half of the value, maybe until here, yeah? Half. I put it over here. Half. Okay? It means that my H2 will increase up to here. And after that, what happens? They have reached equilibrium. They are going to be constant as well. This is what we say as the system has already reached equilibrium. It means that you can see it's dynamic. It is still reacting. Okay, it's still reacting. The rate of forward and the rate of backward reaction, because it's still reacting and the conversion is the same, the concentration of the reactant and the product is going to be constant. Not the same, yeah, constant. And it is a closed system. Nothing goes out, nothing goes in. Yeah. So this is going to be, okay, the graph. Okay. Now, if you look at this particular reaction, and let's say I decide to include catalyst over there. Okay, let's say I decided to include catalyst over there. What do you think will happen? Okay. Is it going to be the rate of forward reaction only going to be increased? We know catalyst increases rate of reaction by, okay, providing an alternative pathway, okay, or providing the activation energy which is lower. So generally rate of reaction will increase. Now my question over here is, it is a reversible reaction. Is it going to increase forward reaction or is it going to increase backward reaction? Any idea? Rico? Increases forward? Not really. Yeah? The catalyst, okay, will increase both forward and backward reaction. Please remember that. This is very, very important. Catalyst will increase both forward and backward reaction because why? The moment you decrease the activation energy, it will make both reactions, forward and backward, to be completed in an easier way. It means it requires less energy. So both also will increase. Now, because of that, nothing will change to the rate of forward and rate of backward. Okay, or you can say both rates are increased, but in the end, both are the same. Okay, both are the same. Nothing will change to the concentration. A concentration is just, you are just going to reach the product or whatever that you want to achieve in a faster rate. That's it. Nothing will change to the concentration of the product or reactant. Okay, and it's still a closed system. Now, what is important over here is, okay, there is no change in terms of position of equilibrium. Later, I'll tell you what is position of equilibrium. Now, all equilibrium, okay, this is what we call as position of equilibrium. Okay, it means the equilibrium, okay, they will take certain position. Okay, And this is going to be explained well, okay, by this guy. Okay, there is a theory, okay, called Chatelier'S principle. Now, according to this theory, okay, according to this principle, okay, any system in Equilibria, okay, when a change is applied, okay, whenever there is a change being applied to the system or to the equilibrium, the position, okay, of the equilibrium will shift. Okay, the position will shift. Okay, to be simple, the position can shift either to the right or to the left. Okay, but the reason why they are going to shift the position is to eliminate. Okay, is to eliminate or counter basically eliminate or counter react, or just put eliminate or remove the change. I'll give you a simple example. Let's say, for example, okay, we have Rico sitting over there. Okay, this is already equilibrium. Okay, the group is already stable. Yeah, they are already like took time to get to know each other and so on. Suddenly, I am going to remove Rico and put him into another group. Okay, I am disturbing the equilibrium. Now, what the system will do, the class, yeah, the class is the system. The class, maybe you guys, okay, will maybe after Mr. Gopi's class, call Mr. Rico back. Okay, basically you guys are going to try to counter react the change. And eventually, Rico may be sitting from there, maybe don't come back to his original position, maybe he just come to this empty seat over here. It means that at least, okay, he just come near to you guys. That is about, okay, Chatelier'S principle. The Chatelier'S principle basically tells us that the system will always try to react so that you eliminate the change. Okay, and these changes, okay, can exist in form of concentration. It can exist in form of pressure. It can exist in form of temperature, but not in form of catalyst. Because catalyst, just now I told you, catalyst only increases the rate of reaction, and they increase both rate forward and backward reaction. So if you look over here, if I, let's say for example, I am going to look at concentration, and I show you using this graph. Now, let's say I suddenly, okay, increase the concentration of I2. Let's say now, okay, I increase the concentration of I2. Rico, what will happen? According to Chatelier'S principle, you need to reduce the concentration of I2. How do you reduce the concentration of I2? By making it to react more, right? So how do you make it to react more? You react with H2 to form more HI. It means the position of the equilibrium will move to the left. Okay, so when that happens, I2 will be used up, and you are going to get more HI, okay, and it will go to that part. Okay, this is going to be trying to eliminate the change. Now, how do I represent this using graph? Okay, you see here, let's say I give you another example. Let's say suddenly I decided to decrease the HI at one point of time, yeah? You see, how do I actually show it in graph? I suddenly, this is HI, and I suddenly decrease the concentration of HI. Let's say this is the time. that I decrease the concentration of HI. See, it was happy over here, and then I decided, okay, to decrease them immediately. Okay, I decrease them immediately. Now, what happens? It's like Rico, you know, pull him over here. So what happened? The system will try to increase it back. Okay, the system will try to increase it back, but cannot come to original again. Maybe up to here. Okay, now you see, how do I increase the concentration of HI? The position of the equilibrium will be shifted to where, Nicholas? Left or right? You need to increase HI. How do you increase HI? Yeah, by forming more, right? How do you form more of this? You react to give you more HI. Okay? So, it means that H2 and I2 will decrease. And you see here, H2 and I2 will not suddenly decrease like just now. They will decrease. But how much is the decrease? 2 moles and 1 mole. If the increase is from here to here, okay, it should be half of it. So I take half of it, maybe up to here. And then this is the time. So maybe up to here. This is what we call the position of the equilibrium is shifted. And this is going to be your equilibrium, the new equilibrium. Okay, I hope you understand this. Now, let's have a look at this concentration, pressure, and temperature. Yeah, concentration I have taught you. Quite easy to understand. I will teach you about this pressure and temperature so that tomorrow you will be able to understand better. Okay, now when we look at this pressure, okay, when you look at this pressure, okay, pressure is only going to be applied for gas system. I give you two examples here. 2HI, all these are gas. They will give you H2 plus I2. And then I give you another example, N2 plus 3H2 to give you ammonia, also gas. Now, always remember, when you have a lot of molecules in one particular volume, the pressure is more. Okay, because more particles will hit the wall of the container, pressure is more. Less particles means, less molecules means, you are going to have less pressure. Okay, now what you need to do is, basically, just look at the total number of moles, 1 and 3. You just do a little bit of maths. 1 plus 3, 4. You just put 2, you put 2. Now, let's say this system has already reached equilibrium and I am going to increase the pressure. When I increase the pressure, okay, according to Chatelier'S principle, I need to decrease the pressure. How do you decrease the pressure? Forming more molecules or less molecules? How do you decrease pressure? Less molecules or more molecules? Less molecules, right? Because less molecules means less pressure. So you need to move from 4 to 2. Okay? So the position of the equilibrium will shift towards less number of molecules. In this case, you are going to form more ammonia. Yeah? Just be patient with me. Yeah? So I'll just show you also. This one, okay? Total number of moles, you see 2. This is 2. 1 plus 1. Now, if I decrease the pressure according to LCP, okay, Chatelier'S principle, you need to increase the pressure. How do you increase the pressure over here? Number of moles are the same. So, no change. Because pressure do not affect the position of the equilibrium because number of molecules are the same. This is about pressure. Yeah, we will go in detail tomorrow. Now, the last part that I want to teach you today is going to be this temperature related. I'll show you okay, for this example. This is going to be exothermic reaction, and they will usually say delta H is negative 92. They will give you this value. Now, remember last time I taught you about the hand method. When it is going to be exothermic or endothermic, you put your hand over there. This is exothermic, correct? Negative. You put your hand for exothermic reaction. Your hand will feel hot or cold? Hot, okay? Exothermic, heat is released to the environment, okay? You are going to feel hot. You put the hand over there, you put hot. You put another hand here. If that is hot, this is going to be cold. This is the first thing you do. When temperature increase, let's say I'm disturbing the equilibrium, temperature is increased. According to Chatelier'S principle, you need to bring down the temperature. How do you bring down the temperature? Hot to cold or cold to hot? Hot to cold. Position of the equilibrium will be shifted, but don't go and say it will go there. You just say the forward reaction is exothermic. The position of the equilibrium will be favoring endothermic reaction. Just the how you put the words only. Okay. Now another last one. Yeah, I'll just give you one more example. Then you can go. Okay. So let's say I have A plus B. To give you C, delta H is going to be positive. And this is an endothermic reaction. You put your hand over there, and this is going to be cold, positive, cold. And automatically you put your hand over here, this is going to be hot. And let's say I am going to decrease the temperature. So according to Chatelier'S principle, you need to increase the temperature. How do you increase the temperature? Cold to hot or hot to cold? So the position of the equilibrium will be shifted to favor. This is forward is endothermic, so backward is exothermic. Okay, so that is the principle. Yeah.